this is a really interesting discussion when you start to get into the connections between transistors and biological channels. At first you might think, how is there any connection or comparison here? But when you look at a low level of this, what you begin to realize is that there's a number of different things that are similar. When you talk about electronics, no one is surprised at talking about I'm going to have charged particles moving around various structures. Positive ion, I'm going to be having, potentially going to have ions and stuff, but we typically aren't looking at that. We're usually looking at electrons and holes. So we're usually talking about negative and positive charges, which are usually perturbations over a larger number of carriers. And again, the same sort of thing happens in a biological structure. We can talk about having a membrane, which is a bilipid membrane, which basically has almost, there's almost no conductance there. It's almost purely capacitive, separating charge on both sides. And then we get this interesting structure, which is a membrane sitting, or this sort of channel sitting in the middle of the membrane. And that channel has the capability to allow carriers to move in both directions. Basically, now we're talking about charged ions in an aqueous solution. Well, this is kind of interesting. In fact, most people are often familiar with this from like chemistry classes where you say, imagine I have a membrane of ions and things kind of equilibrate. It is exactly that experiment, but now in every single little cell. Okay, so this is great. So you're like, okay, I see charged particles, but why does this have any similarity? Well, if I look at a MOSFET, and particularly if it's operating with subthreshold dynamics, or subthreshold bias currents, going from source to drain, and I look at its band structure in between the source and the drain, say for an NFET, I'm going to get a conduction band that looks something like this, where I'm going to get the source and the drain sort of pinned directly on both sides, and I'm going to have a channel in the middle. That's going to be gated by actually a gate which is going to be capacitively coupling into the structure. If it's thick enough insulator, we'll have almost no conduction and no current through there. On the other hand, depends on process, things change, right? Things shift around. But generally that's how you would think about it. And it's basically, in a MOSFET, it'll be flat all the way through. And this potential will change, this channel behavior will change based on the gating potential, on the gating effect. Well, what's interesting is if I look at a slice through the biological channel, I will see something very similar, it turns out. In fact, going through this membrane structure, when the channel is open, I'm going to basically have a potential through the middle here. Now, it's not going to be perfectly flat because there's some interesting structure in the ion dynamics, but for the most part, it's almost equivalently good enough to think of it as close to flat, with some small shifts along the way. But the overall level is going to get modulated by some sort of gating sort of molecule, which basically now is going, typically often will be sensing what is the potential inside the cell, what is a chemical potential inside the cell, or chemical potential outside the cell. A number of different things that it could be looking for or sensing in that way. But it will sort of create a gating behavior which then changes that channel. Now, this is not always the way we've understood biological channels. If you look at the original work that Hodgkin and Huxley did in terms of their really groundbreaking work in terms of doing biological channels for squid axon, where they saw really were able to piece apart all of the action potential dynamics. They kind of saw these things as voltage-controlled resistors, and then there's some rate equations to do the dynamics, and there was some stuff afterwards that they kind of swept under the rug, and most of the time you never see them, and if you do see them, you usually hear people gasping, because there's a huge amount of equations underneath all of it. But there's a different question to be asked, which is to say, well, given that we kind of understand there's a real clear connection between these approaches, maybe a better approach is to say, well, imagine I use a MOSFET transistor for the sodium channel and one for the potassium channel. Now, I could have used an N or a P. Let's go with 2 P's for this point. And then we use voltages to actually supply what is the Nernst potential that would naturally occur in a biological structure because of the change of the ion. So we're actually kind of explicitly forcing it in there.